Okay, let's get back to it. So question 11.3c, I see a couple of ways to do it, no pun intended. The first way would be to do a Markov-Nakhov addition of HBr across the double bond. And so I would take that compound and I would just do HBr, and that would give me the Markov-Nakhov product, this product. And then all I got to do is treat it with an unhindered base to make the Zaitsev alkene. And so I would just use sodium ethoxide or something, sodium ethoxide, and that would give me this product. But there is another way. Another way you could do it would be, again, start with the exocyclic alkene, and you could treat it with aqueous acid, and that would give you the Markov-Nakhov product, which gives you what's called a tertiary alcohol. And then to make the most substituted alkene, all you have to do is an E1 reaction where you just treat it with sulfuric acid, H2SO4, and heat. And that will always give you the most substituted alkene. And so either one would work. I don't see anything wrong with either of these modes of attack. And so why don't we, we'll not do D for now. We'll come back to it if we have time. Let's move on from there and talk about a few of the ways that we learned how to change the carbon skeleton. The good news is that we didn't learn many ways to tamper with the carbon skeleton. Really, when it comes to removing carbons or decreasing the number of carbons, the only thing we covered was an ozonolysis of an alkene or an alkyne. And when it came to increasing the number of carbons in the skeleton, the only thing that we learned was deprotonation of a terminal alkyne followed by treatment with some electrophile, iodomethane we saw today, ethyl iodide, whatever. Okay, those are really the only things that we have. So to rehash, if you have a terminal alkyne and you deprotonate that to make an alkynide, that will act as a great nucleophile. And so if you have a powerful electrophile, as is shown here, that is going to attack this to cause the leaving group to leave. And now you've created a brand new carbon-carbon bond, which I'm going to highlight right here. And for the time being, it says this is the only way that we know how to add carbons to a compound. Nothing more than that. In fact, if you go back to chapter 9, we saw that many times we would start with acetylene and say, well, how would you, convert that into 1-butene or something? Well, the first step would be to treat it with sodium amide to do a deprotonation, and then you would just treat that with ethyl iodide, something like that. It's relatively not complex. As far as decreasing the number of carbons, the only way that we have to do a decrease in the number of carbons is to use ozone, whether that be with an alkene or an alkyne. Remember that when we're dealing with an alkene, we use ozone followed by DMS. And when we use an alkyne, we use ozone followed by water. So it's slightly different. Well, with all that in mind, let's take a look at the first problem here in 11.5. I want to take acetylene and I want to convert it into 2-pentyne. Could anybody answer me just for the first question for part A? Would it matter if I added, because I have a methyl group here and I have an ethyl group here, does it matter which one I add first, the methyl group or the ethyl group?
No.
No, not at all. And so just Emily says, no, just needs to be 2 steps. I agree with you completely. Just needs to be 2 steps, doesn't it? And so we could do either one. Let's just pick the methyl since it's on the left. So we'll go here. And first step, we'll treat it with sodium amide, followed by methyl iodide, and that will give us this compound. Remember to not draw the compound like this, okay? That is wrong because remember that the molecular geometry here is linear. This is a 180-degree bond angle. So don't do that. And next, we're going to add the ethyl group. So we'll do first step, sodium amide, which is a great base. And then in the second step, we're going to treat it with ethyl iodide. So I'll just put ETI. Remember that ME stands for methyl, and that ET stands for the extraterrestrial who went home. No, I'm kidding. It stands for ethyl. And that's going to give us our product, so which looks something like that. There we go. Now in the next one, instead of us adding an electrophile like either one of these, now we're starting with the electrophile. So you have an electrophile. You can see that we have a total of 7 carbons here, but we end up with 9 carbons. So where would I get a 2-carbon nucleophile? The answer is I'm going to treat it with sodium acetylide. And I want you to remember that you can assume that you have sodium acetylide at your disposal. So you can always assume that you have the sodium acetylide ion. So it's just going to do a plain old, that's not a very good curved arrow. It's going to do just a plain old SN2 like that. So this is an SN2. And there you go. You've added 2 more carbons. How do you approach a synthesis problem? It's a little bit different for everybody if you ask around. However, we're all doing the same thing. So how different is it really? You know, we're all doing the exact same thing. But one of the first questions I like to ask is there a change in the carbon skeleton? Gaining carbons, are you losing carbons? If I'm gaining, well, it's going to have to involve a terminal alkyne. If I'm losing, then it's going to have to involve ozonolysis. Is there a change in the functional group, identity, or location? I have to take that into account as well. Solving a synthesis problem requires that you recall all of the reactions and that you have to work through many examples. Never think that you're the only one who has to cover a lot of examples. It's normal. Everybody has to do a lot of practice in order to master the content in organic chemistry. In fact, I would say it would be pretty special if you didn't have to refer to all the different reactions, or if you didn't have to practice, I would say. Anyhow, let's take a look here. It says propose an efficient synthesis for the following transformation. First thing I'm going to do is count 1, 2, 3, 4, 5 carbons, whereas here I have a total of 1, 2, 3, 4, 5 carbons. What am I doing? Mr. Dion's losing it. Let's see, 1, 2, 3, 4, 5, 6, 7 carbons. So you can see that I'm adding 2 carbons. Well, I was also getting ahead of myself in that hopefully you could identify that we need to add the carbon over here. So we're going to deprotonate the terminal alkyne. We're going to treat it with an electrophilic source of 2 carbons, which would be something like ethyl bromide, ethyl iodide. And then if we want to reduce an alkyne to a transalkene, could anybody remind me what the conditions would be to go from an alkyne to a transalkene? Like, let's say I was able to make the transalkyne. So 1, 2, 3.
You would do it with sodium and liquid ammonia?
Absolutely. Sodium metal reduction, right? Sodium and liquid ammonia. And there you go. We've kind of solved the problem in our mind's eye already. Right? First, we're going to have to do a deprotonation with sodium amide, followed by treatment with ethyl iodide, and then we do a sodium metal reduction to make the transalkene. Done. That's it. So we can skip all this and go right ahead to the answer, which is here. And again, I think this is a problem that a lot of my students have mastered already and would be able to answer with relative ease. But even if you were confused, you know, the first thing you would want to do is count those carbons. Do I have the right number of carbons? Do I need more carbons? Do I need less carbons? Right? And then, you know, you have an alkyne, you have a transalkene. Well, there's only so many options that I have available to me. With all that in mind, let's take a look at a practice problem. This is question 11.7. This first one, maybe we'll just do the first couple of them. Then we'll talk about retrosynthesis for a minute. Just looking at stuff here. All right, identify reagents. What's the first thing we should do? count the number of carbons. So we're going from 5 carbons to 8 carbons. So I've got to add 3. Did anybody give me an idea what a good first step would be here? I know you know. I just need a drink of water. What do you got for me? Good first step here.
Sodium amide followed by water workup.
Yeah, in this case, you're on the right track for sure. I would start with sodium amide. 1, 2, 3, 4, 5. Let's put in that proton. So in the first step, you want to treat it with sodium amide. Let's just draw the alkanide. Let's just delete the number 1 here. And let's draw what you get. So you would end up with this alkanide. So sodium alkanide, so 1, 2, 3. Right, you don't want to treat it with water next because then it's just going to go right back to here again. And we want to add those 3 carbons. So what do you think might be a better electrophile if I want to add the 1, 2, 3 carbons? Maybe propyl iodide, propyl bromide, propyl chloride. Any one of those would work. I feel like propyl doesn't get a lot of love. Or sorry, chlorine doesn't get a lot of love. Propyl gets some. But anyway, so why don't we do propyl chloride? And then that's just going to do SN2 on here. And there we go. Like 1, 2, 3. 1, 2, 3. And then to reduce that to the cis alkene, I'm going to use hydrogen and Lindlar's catalyst, just like that. Cool, cool. Good. Let's try one more. I know that I did this. I remember doing this one with my class last semester. I think this is a great problem. I like this problem. It kind of it forces you to step out of your comfort zone a little bit and think about all the different electrophiles that you could have. Because if you just count the carbons on the top, we have 1, 2, 3, 4. Right, there's 5 and 6, I know, but let's just forget about them because they're not really involved. And we have 1, 2, 3, 4, 5, 6, 7. And so if you want to add 3 carbons, you can add it as an electrophile like propyl chloride, but you can also add it as a nucleophile. How would you do that? If you're wondering, well, what if you took this compound and you treated it with HBr and peroxides? That would do an anti-Markovnikov addition of HBr across the double bond, and now you've got a primary alkyl halide. And so if you want to add the 3 carbons, here's what you can do. Instead of using an electrophilic source of 3 carbons, you could use a nucleophilic source. So you could use this alkanide. You could just assume that you have any small alkanide at your disposal. And of course, that's going to react in an SN2 fashion. And that will give us, so let's make sure that 1, 2. That's going to give us this compound. And then if we want to reduce that to a transalkene, all we have to do is good old sodium metal reduction. And you're done. That's it. That's all there is to it. So I'm going to skip the last one for now, because the last one involves some kind of moving of a bromine around the molecule. So why don't we save that? We can maybe do that at the beginning of class on Wednesday. But to wrap up, we'll take a look at a couple more problems today. But just to kind of wrap up, let's just kind of take a peek at retrosynthesis. The last 2 sections aren't really that big a deal for us, to be quite frank. I mean, I don't think any student's life has been changed by inventing their own synthesis problems. If that's something you enjoy, by all means, go ahead and do that. But it's something I've never tested students on, and it just is another way to increase your proficiency in organic chemistry. So let me just scooch ahead here. Just give me 2 shakes of a lamb's tail. All right, retrosynthetic analysis. Retrosynthesis was developed by E.J. Corey at Harvard University. And it means nothing more than if you ever are given a synthesis problem on a quiz or an exam and you are really confused, I don't know where to start. A lot of times what organic chemists will do when they're facing this kind of situation is they'll go backwards. They'll say, okay, well, I know what the product is, what is there anything I could make that product from? So they'll go back one step, just one step, and then they'll say, well, if I know the last step, so could I go forward to this, intermediate or something? And that is a very valuable way of solving problems. Let's say you had this problem here. Let's say I asked you this on an exam. You say, okay, well, I have a primary alcohol or a terminal alcohol, and I want to make an alkyne. I don't know. I'm not sure how to do that. Well, what I can tell you is that you're not changing the number of carbons in the skeleton, are you? You're starting out with 1, 2, 3, 4, 5, 6 carbons, and you're ending up with 6 carbons. Therefore, the only possibility that you would have in this class that you are taking right now, at this point, would be that you would have to have a vicinal dibromide. And you could take that and treat it with excess sodium amide, followed by H2O, and that would give you the terminal alkyne. So now you've solved the last step of the problem, and now the problem becomes, well, how do I go from here to here? Well, the only way I know to get a vicinal dibromide would be to have a terminal alkene, like this. Now you shorten it again. How do you go from the alcohol to the alkene? Well, the alcohol is not a great leaving group. However, I could convert it to a good leaving group if I treated it with tosyl chloride and pyridine. And then if I treat it with a hindered base, it's going to give me this terminal or Hoffman alkene. And there you go. We've solved the entire problem just by going in a backwards fashion. We didn't go forward at all. We just went completely backward and solved the question out loud. And thus, if you look at the total synthesis of this compound, I'm just going to skip ahead here. Here's what it's going to look like. We're going to take that alcohol, convert it to a good leaving group with tosyl chloride and pyridine, followed by treatment with a hindered base like DBU or DBN. I'd accept T-butoxide as well. That gives us the Hoffman alkene. Now you can do the dibromination, followed by the double elimination and the protonation, and you're done. That's it. But again, if you look at going from the alcohol to the alkyne, I would say it's not abundantly clear immediately. And so a lot of times problems will be best solved using retrosynthesis. How many steps is this anyway? And look at it, it's a total of 5 steps. 5 steps. Oftentimes, research groups will do syntheses that are up to 60 steps in a row. And so later on in this class, we're going to be looking at syntheses that might even have up to 10 steps, 10 steps. So oftentimes we're going to employ the retrosynthesis strategy. And that's why it's such a great idea to master it now, to get the concept down so that you're able to use it to the best of your ability and to help you as we move forward in the course. Well, that's a lot of information. Let's try a problem and think about it in terms of retrosynthesis. Let's say you want to start out with acetylene, this little guy here, and you want to make a halohydrin. Well, my friends, halohydrins have only come up once today. We only know one way to make a halohydrin, and that is from an alkene. If you had 1-butene, this alkene, and if you treated this with bromine in water, that, son of a gun, what's going on here? My Apple Pencil spacing out. There we go. That's going to give you the halohydrin. Well, now, how am I going to go from here to here? From a 2-carbon molecule to a 4-carbon molecule. Again, I think the best idea would be to go through the alkyne with 2 carbons, and then those 2 carbons could be added to the acetylene. And there you go. We've gone backwards and we've solved the entire problem. The first step would be to treat it with sodium amide. The second step is to add the 2 carbons using ethyl iodide. That's going to give you 1-butyne. Then we need to reduce that to 1-butene, this compound. And so we're going to use hydrogen in Lindlar's catalyst. If you're wondering, hey, couldn't I reduce the 1-butyne to 1-butene using sodium metal reduction? The answer is no. This will not work. You've got to use Lindlar's catalyst. And then the last step is just to treat it with bromine and water. Give me a thumbs up if you follow me on that synthesis. I don't think that's simple. I think it's interesting. I think it's doable. It's manageable. I don't think anything in organic chemistry is simple. Okay, great. Thanks, everybody. That's great. Well, let me throw this out there to my students. If I have the second problem here, I'm starting with 2,3-dimethylbutane as my starting material. What's the only possible thing I can do at the beginning? What do you got for me? Only possible reaction. Yeah, absolutely. Bromine and light. That's it. It's the only thing we have. Perfect. So we're going to treat this with bromine, Br2, and light. Kind of running out of space here, so I'll just throw it down here. There we go. Wow. So if we want to add that alcohol on the end, I think the next thing we should do is do an elimination. We got two kinds of beta protons. We got this red one here. We also have this green one. If I want to remove the red one so that I end up with, son of a gun, I'll use my blue pen. Where's my blue pen? So that I end up with this compound, how would I do that? I would want to use a hindered base. I'm going to pick T-butoxide just for fun, and that's going to give me this Hoffman alkene. And then for the last step, all I have to do is an anti-Markovnikov addition of water across the double bond. First step, borane and THF, followed by hydrogen peroxide and sodium hydroxide, and there you have it. Hot dog, we have a wiener. Perfect. Give me a thumbs up if you follow me on that one. Again, I don't think it's a trivial problem. Nothing we do is trivial. Okay, good. All right. The whole thing about green chemistry. Here. Well, green chemistry, let's talk about it quickly. It's important. It's 2022. Students, instructors, are, people in industry, researchers are always trying to find ways to make compounds and to eliminate making copious amounts of waste. What can we do to reduce the amount of waste that we make? Well, we can refer to what's called green chemistry, which is guided by 4 principles. The first one, we try to, where did it go here? 4 guiding principles. Prevent waste, use less hazardous substances, so avoid things like mercury, osmium if you can. Use safer solvents. There's a lot of solvents that chemists used to use every day, and now we try to avoid them. Things like carbon tetrachloride, for example, very harmful. And then we try to maximize atom economy. Now, if you're like, what in the heck is atom economy? Is that where I buy some atoms at Walmart or something? No. Atom economy is represented here. Take a look at these 2 hydration of an alkene reactions. One employs oxymercuration, demercuration on the top. The one below it uses just a catalytic amount of H3O+. Well, which one has better atom economy? Check this out. In oxymercuration, demercuration, all these atoms shown in red here, those all end up in waste material. That is not a very good use of all that matter. Whereas if you look at catalytic addition of water using just some acid, then the only thing that ends up in the waste is the H+, but this is a catalyst anyway. So you don't even need a stoichiometric amount. You only need a catalytic amount. So much, much better for the environment. And so we say it has a better atom economy. Less atoms are wasted, end up in the waste in rivers and lakes and streams, the atmosphere, places we don't want chemicals. And so we can always try to use catalysis when we can. We try to avoid using stoichiometric amounts of reagents. Energy efficiency isn't one I think about a lot, but this would mean doing reactions at room temp instead of heating them. That costs electricity to do that. And then renewable feedstocks, if we can use starting materials that come from renewable sources like grain and corn, as opposed to the petroleum industry, then that's going to be more environmentally friendly as well. Well, after all this information, let's say you haven't studied organic chemistry in a while, or let's just say organic chemistry isn't your most passionate subject that you've ever studied, well, how would you increase your efficiency. This is something we can sit around and talk about for a long time, but you know, you've really got to know all the tools. You've got to know all the reactions. You've got to find a way that works for you to memorize them. Personally, I like repetition. I just repeat it until I know it. And you know, this is how we learn languages when we're children. And so I think it's a really good strategy. Other people like flashcards, maybe a mnemonic, things like that. But you've got to find something that works for you. You always want to keep in mind if there's some kind of change to the carbon skeleton, are we moving a functional group around? And as we learn reactions, you want to add them to your toolbox, to what you know, your body of knowledge that's in your brain. You can create your own synthesis problems. I'm going to leave this here as sort of an FYI thing. So I'll just put this in FYI. There are ways to start with something and then go backwards and make your own synthesis problem and trade them with friends. I've never asked my students to do it, but if you think you might find it helpful, my hat's off to you, and be sure to give that a shot. There's an example here. And the last part of chapter 11 just shows you how oftentimes there is more than one correct answer for a problem, especially in Chemistry 3111. However, as the course progresses, let's say one person answers a question in 2 steps and another person answers the same question in 7 steps. Well, the 7 steps might not be wrong, but I wouldn't say it would be worth full credit. And on a multiple choice, if I give you multiple ways that work, you would want to choose the one that is most efficient. We're always looking for the most facile or simplest synthesis, generally speaking, having the fewest steps. Very few exceptions to that. You see here, we're taking this terminal alkene and we're converting it to a primary alcohol. How would you do that? Well, there's a couple of ways. You could just do an anti-Markovnikov addition of water, as you see in the top example or the top reactions. However, another option would be to do an anti-Markovnikov addition of HBr across the double bond and then treat it with hydroxide as a nucleophile. That would work too. They're both 2 steps. I'd say they're both winners. You know, they're both perfectly reasonable. I don't see anything wrong with these. But again, as we progress, if one person solves a problem in 10 steps, it can be solved in 3 steps. We're always going to go with the method that has the fewest number of steps.